This is explanation for test number 16 regarding part 2 of circular motion. So in this test, we are mainly focusing on the applications of circular motion, right? So we'll move on to the first question. A coin is placed at the edge of a rough circular plate with radius 50 centimeter. So let's say, so this is the circular plate and it has a 50 centimeter radius, 0.5 meters. If the plate is rotated at 2 rads per second, so this is omega and constant, they say a coin is placed at the edge. Here, let's say it has a mass simple m. So if you look from a side way, this is what you see, right? So this is the plate. So there you have the coin. So mg and there's r. So the plate is rotated around this axis. Okay. So here what they ask is to do this, the minimum coefficient of friction required, right? So for this case, I'll just first solve this using just the symbols, right? And let's say the radius is r. If you take the force equilibrium to this side, it is in equilibrium, right? So you can say r is equal to mg. Then as usual, just apply F equals ma towards the center. We do this in almost all the questions in circular motion, right? Towards the center, apply circular motion. Right. So what's the force here? You know, in order to keep this as it rotates, in order to keep this without falling off, there must be a force. That force should be friction, right? So here they are asking about minimum friction coefficient. So you know that F can be written as mu r. So whenever they say minimum, maximum, or just starts to slip or something like that, they are talking about a limiting condition, right? They are talking about a limiting condition. So you can apply F equals mu r. So this is the limiting friction or the maximum friction. Okay. Okay, so the friction is the force towards the center. So you can write it as mu r equals ma. This mu r is what? It is equal to mg. Ma, mass cancels off. Then mu is equal to acceleration divided. Sorry, the acceleration you can write in terms of centripetal acceleration. Centripetal acceleration. Let's say r omega squared, right? R omega squared. Then all you have to do is just substitute values. So r is 0.5, omega is 2 squared divided by 10. So when you simplify that, you get 2 squared means 4 times 0.5. That is 2 divided by 10. So you get 0.2. So this is the coefficient of friction required in order for this coin to remain on the edge, right? So this is the minimum frictional coefficient required. So if you have a frictional coefficient more than that also, the coin will remain here while rotating, right? But what they're asking is the minimum friction coefficient, so you can find that like this. The second question, centripetal force required to take circular bend with radius 50 meters by a motor car weighing 50 kilogram at 36 kilometers per hour is. So 36 kilometers per hour, I'll just first convert it into meters per second, right? So it should be 10 meters per second. So they say the motor car is taking a bend, right? And the radius they have given as 50 meters. Radius is 50 meters. So let's say the car is like this, right? So when you take the side view of this car, so this car is balanced under these forces, R and mg. In order to keep the car in a circular path, it requires a centripetal force. So in this case, that centripetal force is provided by the friction acting on the car, right? So let's say that friction is F. So this is the centripetal force. The centripetal force, you know that it is like this, right? F. So according to this, you can just write R equals mg, just thinking about force equilibrium vertically. Then, as usual, just apply F equals ma towards the center, right? So here what they ask is centripetal force required. Let's find that. So that force is capital F. Let's say that is friction. That is the only force towards the center. Only force towards the center. The mass of the car, right? Mass of the car. It is given as 500 kilogram. And for the acceleration, we can use v squared over r. That is the centripetal acceleration. Because what is given is tangential velocity, right? 10. So here you can substitute 10 is squared divided by radius is 50. So you know 100 divided by 50 is 2. 2 times this is 1000 Newton, right? So this is the centripetal force required, which is the friction required actually. Friction force required in order to keep the car in this track while moving at 10 meters per second, right? So in this question, they haven't given any mu or something, right? Mu or r. What's the reason for that? Sometimes students think whether to apply F equals mu r to this question or not. Just remember that this F equals mu r can only be applied, given that this is limiting, only we apply it for the limiting conditions, right? So in this question, there's no limiting conditions, right? So if you remember that graph between friction and applied force, limiting condition is at the top here, right? Then you have the kinetic conditions. Before that, it is just in equilibrium, right? Right? You have to make sure when you apply this equation, you have to make sure whether this problem they are asking in limiting condition or in kinetic condition or just before limiting condition. So this question is regarding somewhere here. It hasn't gone up to the limiting condition. So an easy way to understand whether it is limiting or not, kinetic you can easily understand, right? So to understand whether something is limiting or not, in the question, if they say like maximum, minimum, just it starts to slip, something like that, then it's most of the time the question is regarding the limiting conditions. So you can apply F equals mu r, right? If it is hard to comprehend otherwise, right? Okay. So the answer here should be third one. Right. Let's say third question. When the road is dry, maximum safe speed for a car is 10 meters per second. When the road is wet, it is 5 root 2 meters per second. If the static friction coefficient is mu for when road is dry, static friction coefficient when the rod is wet, right? So you can see they are talking about a maximum speed, right? Maximum speed that you can take the car, you can take the bend, right? So meaning of that is you can actually apply F equals mu r. So that is a limiting case. This is a limiting case. So you can apply F equals mu r, right? So as usual, it is taking a bend. So the car is somewhere here. So now you have F. First, I'll do this just using symbols, right? I'm going to use a proportional method because they are talking about a comparison, right? So you must use proportional methods whenever they say a comparison, when the rod is wet and when the rod is dry. So there are two cases for the same scenario. So you can easily use a proportional method. Don't avoid using proportional methods. Otherwise, if you apply equations twice, then it is going to consume a lot of time, right? So you have to get used to the proportional methods. Otherwise, it is not possible to get answers in correct in a short time, right? Okay. Before using the proportional method, I need to derive an expression for this correctly, right? So you know that this R is mg, right? If you think about vertical forces, normal reaction is equal to the weight of the car. Then, as usual, just apply F equals ma towards the center. So for this F, it is a friction. You can apply mu r. Why? They are talking about a limiting condition, ma. So instead of r, you can put mg equals ma. So they are talking about a velocity. So instead of centripetal acceleration, you can apply v squared over r, right? Okay. So this m cancels off. So you get mu equals v squared over rg. Okay. So we derived an expression for the friction coefficient. But you have to consider two cases. So when you compare those two cases, what's the only difference? What are the variables? You have to identify the variables, right? At a one time, road is dry. For the other case, road is wet, right? And according to that, maximum speed changes. So this is Vmax actually, Vmax squared. So you can see at the two cases, radius does not change. Gravitational acceleration does not change. So according to this, you can say what? Mu is proportional to Vmax squared. Got it? Mu is proportional to Vmax squared. Don't worry about the other stuff, right? Even though you write those stuff, they cancel off. You don't have to go for that much calculations. Use proportional methods. I strongly suggest you to use proportional methods if it is applicable there, right? Whenever there are two cases that you have to compare, you can always apply these proportional methods. Don't use the whole equation always, right? So most of the MCQs you can solve using proportional methods, right? So for the first case, when the road is dry, static coefficient, let's say dry, they say just mu, and the velocity, maximum velocity car can take is 10. So 10 squared. So what they ask is when the road is wet, right? So let's say mu dash. And they have given the velocity 5 root 2 square of that. Then divide mu dash by mu equals 5 root 2 squared. So it is 25 times 2, 25 times 2 divided by 10 to the power 2. So it is 100. So you get 1, 2. So it is 0.5, let's say 1 over 2. So what is that? Mu dash is equal to mu divided by 2. So for the explanation, we took this much time, but when you are solving the problem, you can quickly get these. Actually, from this you can understand that these are constants and remove the constants, right? Then only take the variables. In this question, variables are mu and the velocity, maximum velocity. So once you understand that, you can quickly get the answer for a question like this, right? So the first one is the answer there. Right. Fourth question. A bike takes a bend with radius 39 point. So let's say this is the bend. Then the radius is 39.2 times root 2 meters. Right? So this is the bend. Let's say the bike is here. So the friction on the tires is acting towards the center on the bike. And the speed of the bike, they have given 19.6 meters per second. It is inclined with vertical towards the bend. So you cannot take when you are riding a bike, you cannot take a bend just like this, right? You have to bend the bike towards the center like this. So let's say this line is the bike. So to vertical, you have to bend it like this, right? You have to bend it like this. So the friction, there you have the tires. So the friction is acting to this side on the bike. Then the normal reaction on the tires acting to vertical and downwards acting mg. That is the weight of the bike, right? So the mg is acted on the center of gravity of the bicycle, right? And the man, the whole system, right? So what they ask is the angle. How much should be the inclination when you are taking this bend at this speed? So without this inclination, you cannot take this bend at this speed, right? Okay. So let's see how to find this. So as usual, I'll first just apply F equals ma towards the center. We always do that, right? Right. So friction is the force. So in this case, you can understand that nowhere in the question they mention anything about a limiting condition, right? So this is, you cannot apply mu r in this question, okay? They are not mentioning anything about limiting conditions, right? So using this one, you can find the friction as well, actually. So let's say mass of the bike m, velocity of the bike. I'm not going to substitute values yet. So let's say v squared divided by r. At the end, I'll substitute values, right? So the friction is mv squared divided by r. So instead of friction, you can apply mv squared divided by r, right? Then another equation, if you want, you can think about, if you think about the vertical equilibrium, so you get r equals mg, right? R equals mg. So you have these two equations. Still, we didn't get an equation regarding this angle, right? This angle theta. So how do we get an equation for that? In order to find theta, we need to involve theta. We need an equation involved with theta, right? So for this, I'll just say like this, right? Like this length from here to the center of gravity, I'll take this length as simple x. Let's see what we can do here, right? So here I'm going to take moments around center of gravity for the system. Mg goes through g, right? So you don't get a moment from mg. But if you think about f, what's the perpendicular distance to f? X cos theta, right? This is the adjacent side. So here you get theta, then x cos theta. Actually, it is to the opposite side actually. So I put a minus value there. It is the opposite side. Minus fx cos theta plus, when you take r, another force is r times this length. So this length is what? X sine theta. R x sine theta. So the bike is balanced like this at this moment, right? So you can say this whole thing is equal to 0, right? So here you can get rid of x. So you know that r sine theta is equal to f cos theta, right? So now we have three equations. So instead of r here, I can put mg. So r is equal to mg. I can put mg sine theta equals, instead of friction, I can put mv squared over r and cos theta. M cancels off. Sine theta goes cos theta, sine theta divided by cos theta, that is tan theta, is equal to v squared over rg, right? Now you just have to apply, substitute values, and you can find the angle theta. So if you substitute these values earlier, then the question is going to get complicated. Those calculations will be complicated, right? So that's why I didn't substitute those values, and at the end you can substitute. It will be a bit easier, right? Right. So the velocity, that is 19.6, and it is squared, right? Divided by radius. What's the radius? 39.2 times root 2. In the question they say you have to take gravitational acceleration as 9.8, not 10, 9.8. So they are saying that intentionally to make it simpler, the calculation simpler, right? Because this is an MCQ, right? So 9.8, 2 times 9.8 should be 19.6, right? So 2, then 2 times 90.6 is 39.2. So I can get rid of all these. So end up with 1 over root 2. So tan theta is equal to 1 over root 2. So what's the value of theta? If tan theta is 1 over root 2, value should be what? Tan inverse 1 over root 2. Got it? If tan theta is 1 over root 2, value should be tan inverse 1 over root 2. Not 45 degrees, right? In order for the theta to be 45 degrees, this should be 1, right? Tan theta should be 1. Here, tan theta is 1 over root 2. So you can write it like this, tan inverse 1 over root 2. So the answer there is fifth one. Okay. Fifth question. A vehicle moving at V takes an inclined smooth bend with radius r and width simple b. Height difference required at both ends of the path or bend is, right? So here they are taking a bend. But in the question, the bend does not have any friction, right? So if there's no friction, we don't have a force in order to create centripetal force. You know, the mass requires a centripetal force to go in a circular path. But if it doesn't have a friction towards the center, then we cannot create a centripetal force. So in order to create the centripetal force, in the question, what they have done is they have created a bend like this, right? Bent like this. So here h, they say width of the bend as b. Then the vehicle is like this. right? So if you mark all the forces acting on this vehicle, there's no friction involved in this question. So the vehicle would be moving in a circular path like this, right? So the center is somewhere here, right? Somewhere here, right? Let's mark forces. Normal reaction force. We have the normal reaction force. Then we have the weight, mg. What else? That's all, right? Let's say this angle is theta. This angle is theta. 90 minus theta. Then here theta. This angle also is theta then, right? 90 minus theta, 90 minus theta. Theta. Then this angle also should be theta. Right. So for this question, for this moment, you can consider vertical equilibrium. Vertically, there's no movement, right? Movement is only horizontal. So if you think about vertical motion, you can see it is not r now, it is inclined. So you have to take r cos theta. So r cos theta is equal to weight, mg. R cos theta is equal to mg. Then as usual, just apply F equals ma towards the center. Remember, center is here, right? It is in a horizontal circle like this. So that you have to always do that, right? You always have to apply the equation towards the center. Then the question gets easier, right? Because you know the acceleration, you know the equation to write the acceleration towards the center, right? Okay, here, what does create this centripetal force? So you can see that this force here it is r cos theta, but to this side you have a component r sin theta. So that is the only thing, only force horizontally. So which becomes the equivalent force or the resultant or the unbalanced force towards the center, right? So that is r sin theta. We don't have any other forces. So using this r sin theta, the vehicle can go in a circular path. So this only the r sin theta is what contributes for the centripetal force. It is actually centripetal force in this case, right? So now r sin theta is equal to ma. For a, you can write v squared over r. So the radius of the bend, I think capital R, right? So you get v squared over capital R, right? So we have these terms. So in the question, what they ask is an expression for this h. So how much should it be lifted from a one side, right? So this application you can see in railways, right? So when they have to take when the train has to take a very deep, I mean high bend, right? When the curvature is high, usually they one rail they lift it up like this, right? They lift it up like this, so the train can go over that. Okay. So let's say this is the second one, first one. So first divide by second, right? So r sin theta divided by r cos theta, r cancels off. You get sin theta divided by cos theta tan theta is equal to. So here you have v squared over r and m cancels off, right? V squared over capital R and here you have g. M cancels off, v squared over capital R g, right? We get that equation, an expression for tan theta, right? So when you get tan theta, what can you write? So tan theta is equal to opposite divided by adjacent. So that is h divided by b, v squared over rg, right? Then you can put r to the other side. So you get h equals V squared B divided by RG. V squared B divided by RG. So by this much, you have to lift one side of the rod. So you can create the required centripetal force, that is R sine theta, towards the center. Okay. So without that, it is not possible to take a bend without the friction, right? Here there's no friction, right? Right. Sixth question. A mass is attached to a string with length simple L. Mass moves along a horizontal circle. So the circle is like this. Let's say this is the ceiling, and this here you have the the string forms a conical shape, right? So they say string makes an angle theta with the vertical. The time period of the mass is, so you know what they're asking is to complete one cycle, the time period. I'll just put a new unknown, that is simple r, right? So in this question, they are asking about the time period, the time required to complete the one round, right? How do you find that? First, mark all the forces. This is the free body diagram for this mass. Weight, another force is tension, capital T. Weight and the tension. Right? So you can see this angle is theta, right? So first I'll just apply vertically. You can see there's no vertical motion. The motion is only horizontal, circular. So vertically, you can say T cos theta is equal to mg because there's no vertical motion. Then I'll apply F equals ma towards the center. Center is here, right? Not here. Center is here. This is the circle. Towards the center of the circle. Right. So in the question, since they are talking about time period, I'll use r omega squared for the centripetal acceleration, right? First, see that. Okay, so to this side, what's the force? Only force is to the component to this side is t cos theta. To other side, it should be t sine theta, right? T sine theta. That is the only horizontal force. And it's the unbalanced force towards the center. It is equal to mass times acceleration. For the acceleration, I'm using r omega squared. Okay. So for this r, if you want, we have to write that in terms of L. We'll do that later, right? Okay. So let's say this is the first equation, second equation. Just divide second by first. Tt cancels off, sine theta divided by cos theta, tan theta equals, mass cancels off. Here you get r omega squared divided by g, right? So when it comes to these kind of problems, these are a bit complicated for a inexperienced student, right? For a new student, these could be complicated. So it is better to use symbols first when you are doing calculations. Don't just substitute values first, right? Okay. In this question is based on symbols actually, so it doesn't matter, right? So here you have tan theta equals r omega squared divided by g, right? I'll subject omega squared. So omega square is equal to G tan theta divided by R. Okay. So what is omega in terms of time period? 2 pi divided by capital T squared. So that is omega. Okay. Remember that. Okay, we'll do that later, right? We need to subject this capital T actually. So we have G tan theta divided by R. For the R, I'll subject, so you can see from this triangle, R is what? This is the opposite side, this is the hypotenuse. It should be L. This R is equal to what? L sine theta, right? This is L and opposite side is L sine theta. Okay, I'll subject that here. That is R is L sine theta. Okay, so this is equal to 4 pi squared divided by capital T squared. Okay, now I am going to subject capital T squared. Just cross multiply, put all the terms to the other side. 4 pi squared L sine theta divided by G tan theta. 4 pi squared L sine theta divided by G tan theta, that is equal to T squared. So here you have 4 pi squared L sine theta divided by G. This tan theta, what is it? Tan theta? You can write it as sine theta divided by cos theta, right? Then this sine theta cancels off. So at the end, you get this equation. T squared equals, cos theta goes to the up, 4 pi squared L cos theta divided by G. Take the root of the both sides, you get 2 pi L cos theta divided by G root, right? So this is the expression for the time period, 2 pi L cos theta divided by G, right? 2 pi L cos theta divided by G. So that is the expression for the time period, right? Actually, you need to practice doing these questions, right? Otherwise, at the exam, at once you cannot do this. So under applications, you need to carefully practice under each applications, right? When it comes to circular motion. Seventh question. Mass of 0.1 kilogram attached to a string of length 0.5 meters is rotated in a vertical circle. If the velocity at top of the circle is 6 meters per second, tension of the string at top is, right? So this question is different compared to the previous questions because this is a vertical circular motion, vertically, right? Questions before this, they were horizontal circular motion. So let's draw the vertical circle. This is a vertical, right? Not horizontal. Okay. So they have given at the top velocity of the particle as 6 meters per second. Radius, it should be the length of the string, which is 0.5 meters. So at the top, what they ask is tension. So you can draw the string like this, then you get the tension, right? Let's say capital T. So what they ask is capital T. Right, let's mark all the forces on this mass. First, I'll just use symbols, right? So M. So you have a weight mg and tension downwards. So just apply F equals ma downwards. We are doing the same thing, right? Like towards the center, I'm applying F equals ma. Right? So since it's a vertical circular motion, you have to understand that mg should be like this, right? you need to understand how these forces are written, right? For a vertical circular motion, right? So these are the two forces. So downwards, what is the unbalanced force? T downwards and mg. T plus mg. Okay. Since they have given a v, I'm using v squared over r. So this is based on symbols, right? So what they ask is tension. So the tension should be mv squared over r minus mg, right? Okay, so the mass they have given as 0.1 kilogram. Now we are just doing the substitution. So here 0.1, velocity 6 squared divided by radius 0.5 minus m means 0.1, then you have g, that is 10. So this is 1 over 5, right? So this is 36 divided by 1 over 5 minus this is 1. So you get 36 minus 5 divided by 5. So 31 divided by 5. Let's see what it was. What is it? Is it going to be 6.2? Sorry, 6 point. So 2, yeah, 6.2. Okay. So the tension at the top of this motion is just 6.2 newtons, right? So remember, if you just correctly mark the forces for any question, right? For correctly mark the forces and follow the methods to apply F equals ma correctly in terms of correct vector knowledge, you will always get the correct answer, right? Eighth question. Speed of a particle moving in a horizontal circle inside a smooth cone at a height of 0.1 meter is. Okay. So you have a cone like this, and they say it is a smooth cone, right? So inside this cone, in a path, it does this circular motion. You can see that the surfaces are smooth, right? So how, in order to have a circular path like this, there must be a centripetal force acting on this towards the center. Center is here. They have given that this height is 0.1 meters. 0.1 meters. But first I am going to use symbols, right? So let's say the radius of this is r, and let's say height is simple h. And I'm taking this angle to be theta. And the velocity, have they given a velocity? What they ask is the velocity. So in order for this to happen, what they ask is the velocity, right? So capital R is like this. If you take this to be theta, then in this plane you have the circle, right? Then theta, 90 minus theta, you get theta here, right? You get theta. If you draw like a 2D diagram, then it is easy to understand, right? Okay, let's see. So all you have to do is correctly mark all the forces acting here. So mg is there, then you have the normal reaction force. That is normal to the surface. There's no any other forces acting on this particle, right? There's no friction here. Only R and mg. Okay. So as usual, I'm going to take the vertical equilibrium. So according to the vertical equilibrium, mg is balanced by not by r, right? But r sine theta. Vertical component is r sine theta. Horizontal component is r cos theta. So you get r sine theta. So that is equal to mg. to the vertical direction, it is in equilibrium, right? Then horizontal. What do you have? So towards the center, there's an acceleration. So it is not balanced, right? There's an acceleration. So I'm applying F equals ma. So towards the center, you get r cos theta, right? R cos theta. Here you have theta, right? R cos theta. Then that is, I'll write mass acceleration. I'll write it as v squared divided by r. This r, right? V squared divided by r. So we are doing the same thing, right? Just apply the equation correctly towards the center. Then apply to a mostly perpendicular to this direction. Then remaining part is just doing calculations correctly, right? Okay, so let's say this is first equation. Second equation, I'll just divide first by second. So r cancels off, sine theta cos theta, you get tan theta is equal to g, m cancels off, g divided by v squared over r. Then you can flip this. This is the main division. You can flip this. So you get gr divided by v squared for tan theta, right? So tan theta is equal to gr divided by v squared, right? So here what they ask is v squared. First, I'll just write tan theta in a different way in terms of these lengths, right? So what is tan theta? Just think about this triangle, this triangle. So here you have theta, opposite side is r, adjacent side is h. So instead of tan theta, you can put r divided by h equals gr divided by v squared. R cancels off. You need to find v, so I'll subject v squared. You have g h. V squared is equal to gh. G is what? 10, right? H is height to the circular motion, circular path. So that is 0.1. So you have 10 times 0.1, that is 1. So V is equal to 1 meters per second, right? So in order to have this motion, you need to have a speed 1 meters per second. So it would have a circular path, circular motion above the ground, that is 0.1 meters above the ground, right? If you increase the speed, let's say you increase the speed, then this would have a circular motion above this, right? If you lower the speed, then it falls a bit, falls below, right? Then it still would keep the circular motion. So that's what happens there. Ninth question. A motorbike of mass 200 kilogram moves in a circle inside a cylindrical well with radius 11.25 meters at a speed of 20 meters per second, right? So we have this cylindrical well, right? Like this. And they say radius is 11.25 meters. So let's say this is the motorbike. And on the motorbike, there's normal reaction force, and there's a friction, and there's the mg. So these are all the forces. And also they have given the friction coefficient, mu, as 0.5. So the question what they ask is friction, right? So this is a good question to understand that limiting or equilibrium frictions, right? Okay. So in this question, actually we don't know whether this is a limiting case or just an equilibrium case, right? So you have doubts whether to apply this equation or not, right? So to identify whether it is a limiting condition or not, what should you do? Anyway, you have to apply this and check, right? Okay. Before applying that, I'll just apply this equation. F equals mv squared over r. So the mass they have given 200 kilogram. Velocity 20 squared divided by radius 11.25. Okay, 11.25. So this is the not F, it is R, right? Towards the center you have the normal reaction force, that is capital R. Not F, right? Towards the center you have the normal reaction force. Right. Then I'll just substitute this here. So mu they have given as 0.5. 0.5 is 1 over 2. R is this much. So 20, 400. 400 times 200. 8 something, right? 0, 0. So you have 4 zeros. 80,000. Divided by 11.25. So if you divide it, you get 40,000 divided by 11.25 Newton. So if this is a limiting condition, we get a limiting friction or a maximum friction of this much, 40,000 divided by 11.25 Newton. Okay. But if we consider vertical equilibrium, what are the forces? Friction minus mg. So the friction is equal to mg. Okay. So let's say if friction is equal to mg, then you just have to find mg, right? So here you have mass is 200 times 10. So we have just 2000 Newton. Got it? Now the friction required is just 2000 Newton. We don't need this much friction, right? Even if you divide this, you can see that this is a larger value compared to 2000 Newton. So you don't need this much friction. This much friction is enough to keep the motorcycle in balanced vertically, right? So it would have the circular path, horizontal circular path. So I'll explain this further using the graph, right? Famous graph, FP, friction and applied force. So the graph goes like this. So at the top, we have that value, 40,000 divided by 11.25 Newton. So that 2000 is somewhere here actually. This friction is enough in order to balance this mg, right? We don't need this much friction. So friction is equal or is less than the limiting friction always, right? So you need to understand this concept clearly about the friction. So the answer is 2000 Newton, right? Third one. 10th question. A small object is placed on a circular horizontal plate table that rotates around its axis. So let's say this is the table, this is a side view. So in this case also, there are two cases that you have to compare. So it is better to go for a proportional method, right? So before going for the proportional method, I'll just derive an expression. You cannot remember each and every equations, right? So you should be able to derive this quickly. Okay, normal reaction, mg, then you have the friction, F. So in this case as well, just apply F equals ma towards the center. They say just it starts to slip. What does it mean? Just it starts to slip. It means this also is limiting condition, right? Limiting. So you can apply mu r. So the friction is what causes a centripetal force. So you can apply mu r, limiting, right? So it is equal to ma. Then if you think about vertical equilibrium, r is equal to mg. R is equal to mg. Right, I'll just substitute it here first. Instead of r, mg, ma. For a, I'll just substitute. Since they are talking about omega, I'll substitute r omega squared, right? Then you get this equation, r omega squared equals mu g. So according to the question, what they change is distance from the center. So basically they are changing this r, right? So according to r, what changes is omega. They are not changing the surface. So mu does not change, g does not change. So only variables are radius and the omega, right? So you can say constant is equal to radius omega squared. Okay, right. So if you take it like this, you can say omega squared is equal to k divided by r. Oh, as a proportionality, you can write it as omega squared is inversely proportional to the radius. Okay. Omega square is inversely proportional to the radius. Right. So in the first case, they say just omega and the radius, let's say r. So you can write it like r root, right? Let's say this is the first part. Then at the second case, let's say omega dash is proportional to 1 over. Now the radius is doubled. So you can write instead of r, you need to write 2r. This is the second proportionality. Now just divide this and find omega dash. That's all you have to do. So omega dash divided 2 by 1, right? Omega dash divided by omega is equal to, omega dash means 1 over 2r root omega r root. Okay, so r cancels off. You have 1 over root 2. Put omega to the other side, you get omega divided by root 2. So that is the omega dash. Omega divided by root 2. Omega dash, right? So the answer should be first one there. So in this question, what you can see is, if you increase the radius, okay, right? Radius means radius of the circular path. Increase the radius, you cannot rotate at a higher speed. See that? When you increase the radius, you need to lower the omega in order to keep this in this circular path, in that circular path, right? So you have to pay attention to those as well. You don't have to remember each and everything, right? Like when you get a question, you need to be able to quickly derive that, right? If you remember, it's better, but you at least you need to be able to like quickly derive the necessary equations, right? Right. 11th question. A particle attached to a string with length r moves in a vertical circle. Vertical. If the tension of the string just becomes zero at the top of the circular path, speed of the particle when the string is horizontal, right? Okay, so this is a vertical circle, right? and at the top, what happens is, you know that it is attached to the string. So the forces are mg and the tension, right? But at the top, tension becomes 0. Here we don't know the velocity, let's say v1. You know, it came from like this, right? When the string is horizontal, it is like this. So let's say at that moment velocity is v, and let's say tension is t or something, t, right? Here it is 0, right? Here there's a tension. So what should you do when you get a question like this? So you need to compare two positions of the vertical motion. So additional to applying F equals ma towards the center, there's one more thing you have to do. You need to get energy equations, right? You need to think about potential energies and kinetic energies, right? First, I'll just apply for this moment, let's say first moment, and this is second moment. Actually it came like this, right? But I'm taking here one. I'll just apply towards the center. Center is here, right? Towards the center, F equals ma, right? So what are the forces? Weight, mg downwards, tension downwards. Mass is just, I'll take it as m. And velocity, which equation should we use? It's better to use this one, right? V squared over r. Because we need to deal with kinetic energies here. Linear kinetic energies. Right. So they say that this t dash is 0, right? This is 0. So you can see mg is equal to mv squared over r. Then mm cancels off. Then we get an expression for v, right? V squared is gr. Root of that is equal to v. You can get this expression, right? So this is not the velocity they ask. The velocity they ask is velocity here. But we know velocity here, right? In terms of g and r. Then you can say energy at 1 is equal to energy at 2. That is the energy conservation. Energy at 1 is equal to energy at 2. Energy conservation, right? Right. I'll just write energy at 1. Before writing that, you need to have a P equals 0 line. Let's say this is P equals 0 line. Right. Energy at 1. What is that? mgh, this is mgr, right? Plus kinetic energy, half m v1 squared. Half m v1 squared. So this is the energy at 1. Then at the second point, potential energy is 0, right? Kinetic energy is half m v squared. Okay. If you want, you can get rid of m. So you have gr plus v1 squared divided by 2 equals v squared over 2. Then multiply the whole equation by 2. So you have 2gr plus v1 squared equals v squared. So what we need to find is v, right? Earlier we found a value expression for v1 in terms of g and r. Then just substitute it here. So what is v1 squared? It is just gr, right? Then we have 3gr v squared. So v is equal to 3gr root. Got it? So if you have this much of velocity here, tension just at the top will be 0, right? So in order for that to happen, we need to have this much tension, this much velocity when the string is horizontal. Okay? Right. 12th question. A motor car with mass simple m moves at constant speed v over a concave bridge with radius simple r. So what is a concave bridge? Should be like this, right? Concave bridge. So the motor car is here. So here you have the bottom of the bridge, right? So this also is regarding vertical circular motion, right? Convex bridge means like this, right? Here you have the concave bridge. And the motor car is moving at V. Radius is R. Radius is simple R. Then there's normal reaction, let's say capital R. Then downwards you have mg. This is radius, right? Okay. So as usual, all you have to do is just apply F equals ma to towards the center. Since you don't have to compare two cases, you don't have to apply energy conservation, right? Just apply this towards the center. So you get R minus mg. I'm applying F equals ma, right? Towards the center. So you have towards the center R, mg downwards, so minus mg equals m. So how do you write the acceleration? Centripetal acceleration towards the center, that is v squared over r. Then what do you get? R is equal to mg plus mv squared over r. Got it? So it should be the first answer. They are only asking about normal reaction force. So if for a convex bridge, you would get like something like mg minus mv squared over r. So you in this case, centripetal acceleration is towards the downwards, right? Because center is here. So you apply F equals ma downwards for this case. Here upwards. 13th question. A smooth circular pipe is placed vertically. Vertical circular motion, right? A small particle placed at top of the circle inside the pipe is released. Force exerted by pipe on the particle when angular displacement of the particle is theta. Okay. So I'll just draw half of that, right? We don't need the whole thing. So you can see here you have the angular displacement theta. So the answers should be only in terms of mg, right? Mg and theta. So I'll just introduce these terms. V, capital R, you have mg, like this. So then there's here as well. Here it is just released. Okay. Here you have two cases. So you need to understand that you might want to apply energy conservation here, because just by applying a one equation here, you cannot get rid of these terms, right? Right. Anyway, I'll just let's say this is first case, second case. First case, second case. So I'll just apply energy conservation, right? So say mechanical energy at 1 is equal to mechanical energy at 2. So for that, I'll draw P equals 0 line, this line. Right. So at 1, so let's say radius is R. Okay. So here, potential energy is mgr. Kinetic energy is 0, right? It is released from here. Then at here, potential energy is what? You need to take this vertical height. You know that this radius is r, right? Vertical height is this much. So how do we find that? This is the adjacent side of this triangle. So you get r cos theta. So you get mg r cos theta, right, for this. Plus, then there's a kinetic energy, half mv squared. Okay. Then I can get rid of m, divide the whole equation by mass. Here you get gr equals gr, I'll put gr cos theta this side. You have v squared divided by 2. I'll take gr out of this. So you get 1 minus cos theta. Then you can cross multiply by 2. Then this is equal to v squared. Take the root. Right? Here we have an expression for velocity. Velocity here. Okay. So I just derived that expression. So what they ask is force exerted by the pipe, which is capital R. What they are asking is an expression for capital R. Okay. So what do we do? Now we have to apply F equals ma to this direction or this direction. Always towards the center, right? You can apply this to the other direction, but it will be confusing, right? So it's better to apply always towards the center. It is not a rule, right? But recommended to apply always towards the center of the circle. Okay. F equals ma. So what are the forces towards the center? This is theta and this also should be theta. Then you get mg cos theta. Mg cos theta towards it. Not mg, right? Mg cos theta. Then minus r. It is to the other side, right? Minus r equals m. I'll use v squared over. I took the radius as simple r. So what they're asking is capital R, right? So we have mg cos theta. I'll take this to the other side because they're asking about capital R. Right? Then you just have to substitute v from here. So you have mg cos theta minus m divided by r. What is v squared? V squared is 2gr 1 minus cos theta. So this is equal to normal reaction, capital R. Then it is just a simplification, right? Right. Then these r cancels off. If you want, you can take actually mg out. Before that, I'll just do the simplification. Mg cos theta minus, you have 2 mg minus minus plus 2 mg cos theta. This is equal to capital R. Then 2 mg cos theta, 3 mg cos theta minus 2 mg equals capital R. Then take mg out. You get 3 cos theta minus 2, right? So this is normal reaction force, mg 3 cos theta minus 2, right? So it is the normal reaction force in terms of mg and theta at this point. So the answer should be 3 cos theta, right? Fifth one, right? Answer should be fifth one there. Right, 14th question. A particle placed at the top of a smooth hemisphere is released. Angular displacement theta of the particle when the contact of the particle with the surface of hemisphere loses. So it is similar to the previous question. I'm keeping it like this. So in this question, what they say is at this moment, like when it is theta, they say contact loses, right? Contact losing means normal reaction force becomes zero. So that's what it means to contact losing, right? normal reaction becomes 0. Earlier we found an expression for normal reaction, this one, right? So what do you have to do? Just make this 0, right? R is 0. So mg cancels off. So you get 3 cos theta minus 2 is equal to 0. Then 3 cos theta is equal to 2. 2 goes to the other side. Then cos theta is equal to 2 over 3, right? I'm not going to derive the whole thing again. I have to do the same thing again, right? Then just make it 0. Okay, so you can write this theta as cos inverse 2 over 3, right? So that's the value there. Right, 15th question. A horizontal circular table rotates around its symmetrical axis at uniform angular velocity. We have a person here and a mass here and a person on the ground. He is A and he is B, right? Observe A is on the table, observe B is on the ground as shown. Force acting on the mass is, right? So you can see this mass, there must be a force. In order to have a circular motion, there must be a force acting towards the center. Acting towards the center, right? But A also is on a non-inertial frame. B is in an inertial frame. A is in a non-inertial frame. Because both A and simple M are at the same frame, there cannot be a relative motion between them, right? So A does not notice that simple M is moving, right? So he doesn't see this velocity. This velocity, he doesn't see that. He doesn't notice that, right? This velocity is only seen by B, right? So if there's no velocity to this side, according to this equation, so according to A, right, this velocity is 0. So if velocity is 0, according to A, there's no centripetal acceleration towards the center on this mass, simple M. Okay. But if you think about B, B is on the ground. He is in an inertial frame. He sees this velocity. He sees this rotates, right? So he sees the tangential velocity, or it can be angular velocity. B sees that. So none of these are 0, right? So according to B, he sees the centripetal force. It is non-zero, right? So the answer should be what? 0 according to A, that is correct. And according to B, pointed towards the center. Yeah. According to B, it is pointed towards the center. According to A, it is 0.